speaker, Professor Tomizuka, and thank you for visiting us, visiting IRIM. Thank you.
Thank you, Professor Zhao. Thank you for inviting me to Georgia Tech and arranging this opportunity to talk with you. And probably I visited Georgia Tech several times in past, but the last time, probably it was still many, many years ago, Professor Zhao just introduced me that I joined Berkeley in 1974. That's 50 years ago, so it's a long time. Probably I should have graduated or retired by now, but the bright student coming to my lab just keep me going. So I think I'm hard to catch up what they are doing, but they are doing great work. So I'm quite happy about this situation. Sooner or later I will retire, but not this year, next year, next year. I'm still getting a new PhD student. So the title is From State Space Control to Intelligent Machines, 5 decades of my journey. So give you some idea how the things have changed. I joined in 1974, and to me, 1960s, 1970s, when I started jumping into this control field, that was an exciting area. US, Soviet Union then, were kind of race space exploration. So lots of interesting control theory came out. You don't know the name even, maximum principle, linear quadratic control, Kalman filtering. I still teach those subjects, stability based on adaptive control. So that's on the more methodology side. But in terms of utilizing the methodology for real applications, we need a computer. And when I came to MIT, department has IBM 1130. It's a computer, okay, with this big card reader. Okay. And also, in the lab, I had PDP-8. Probably name doesn't make any sense to most of you, but PDP-8. That's a real-time mini computer, and I use it for my experiment. So, and also I left MIT in 1973. So HP came up with so-called HP45, handheld programmable calculator. So I thought that that's great. So this should last for some years. So I purchased one when I left MIT, but it didn't last long. Okay. So when I joined, I found PDP-7, and we got LSI-11, and computer became smaller and smaller. So that's on information technology processing side. Then hardware side, I was lucky to be in mechanical engineering, because also around that time, there are lots of interesting things introduced from control point of view. IBM came out so-called Winchester Hard Disk Drive. Then you can store lots of memories. It's the computer device, but it's incredibly mechanical device. And of course, robot was becoming very popular. And FANUC Corporation, it's probably one of the world's largest robot manufacturer in Japan, started in 1972, about at the same time I joined. So naturally, my research activity at Berkeley kind of evolved to synthesizing those three: methodology, computation, hardware. And maybe it's nice to talk about what happened. This is something when the computer, my lab in 1970s. Okay, we had some old mini computers, and at the beginning, I had some robot hard disk drive, and also 1980s, California was interested in automated highway systems. So I joined that group, taking care of so-called vehicle lateral control. So that's how I got involved. And the vehicle control. Then by 2015, I have my home ground is always control methodology. Having control methodology in the center, when I realize my lab, I'm surrounded by all kinds of hardware and having all kinds of fun with students. So there are lots of things from machining, machine tool, robot, and steering system, and so forth. And so this is my lab now. And I have still something close to around 20 PhD students, half of them looking into intelligent industrial robot, and the other half looking into autonomous vehicles. As a tool, we have all kinds of control methodology, but recently machine learning and AI has become a very important part. So I might call this a control-oriented mechatronics group. So we have on the top the methodology part, decision-making, and then I have electronics information technology, and then physical systems started with this kind of thing. And now typically we deal with this kind of hardware. And this is kind of time axis 1970, 1980, 1990. But the most recent addition to the decision-making toolbox is AI machine learning. And for the information technology side, all kinds of things, IoT, GPU, computer, DPU, VR, AR, all kinds of things we are utilizing. So now, we are there, and we have two pillars. One is intelligent robot, industrial robot, and I will introduce some of them today. And human-robot collaboration is one interesting subject we have been doing for at least the last 5 years. And then classic robot problem, but looking from a little bit more new methodology point of view. The impedance control, multi-agent interaction, it's not necessarily a new problem, but we can apply those techniques to new environment. Autonomous driving is area where we can integrate model-based control and machine learning. So something called the zero-shot deep reinforcement learning. This is how you can make a simulation to real gap filling. You train some reinforcement learning the strategy by simulation, but when you apply, the situation may not be exactly the same as in the training environment. So we would like to have nice gap overcome. So that's zero-shot, essentially implementation. And autonomous driving, there are lots of aspects from planning, control, and also real-time collision avoidance, obstacle avoidance, how those things can be put together and for self-operation. And one interesting one we are doing is AI laser. Sony is interested in this type of project, and they are supporting the research. It's a kind of game, okay, but instead of doing race on the real circuit, it's a kind of esports kind of idea. Okay, so let me give you some idea for each project. And first project is safe and efficient robot collaboration systems for next generation intelligent industrial co-robot. This project was sponsored by NSF, and many people graduated. And one key person was Chanliu Liu. She is now an assistant professor at CMU. And some of the things we have done this project has been in the book we published, Design Robot Behavior in Human-Robot Interaction. And human-robot collaboration there are lots of reasons. Manufacturing moved from mass production to flexible automation. Instead of producing the same kind product, but many kinds of product. So their flexibility is really important. Intelligence was important. So there are lots of opportunities for control AI people to do something interesting. And one of them is co-robot, how you can make robot and human collaborate. And robot used to be just for mass production, but as we move to flexible automation, we would like to see more interaction of human and robot jointly accomplishing tasks. So this is more traditional way of utilizing robot and to rigid and repetitive task. It's for mass production. But from flexible production line, for each car, you might need to put different tire. So there, some human can do a very great job. Human is still the most intelligent machine and also versatile. So, but human can be easily tired. Robot can work 7/24, so we can take advantage of those aspects. So one way to envision future factory is there are all kinds of human and robot interactions. There may be some part they are working at the same station, but the other part, human and robot is making one line and doing different things. So both human and robot work together. And in designing the nice human-robot systems, we would like to emphasize both efficiency and safety. Having a robot very close to the people, we have to be very careful. And so design objective and achieving design objective efficiency in terms of the production efficiency, but do real things, lots of things in real time, we need to make sure that computation does not become barrier. And when we have human has lots of uncertainties. Robot has to be careful. So some human make some motion which the robot didn't think about. That has to be quickly recognized and taken care of. So question is how to design the behavior of a co-robot in dynamic uncertain environment and varying human dynamics and the limited computational efficient capacity. So that was kind of challenge. And to answer to that question, one system that we introduced was so-called CEROX, Safe and Efficient Robot Collaboration Systems. It essentially has got 3 modules. One module is environmental monitoring. So environmental monitoring, big part is watch what human may be doing. And once this, you might call this as a social perception module. And if you have perception, how the other one will be making some further motion. You have to predict. Prediction has to come. And then prediction has come, then first it has to be transferred to planning. What kind of plan should be made? And make a good planning, we need to have a task module which is dedicated for task planning. So in here we have some motion skill library and we do online task planning. Just assembly what kind of sequence we should follow is a good question. Then once we figure out, make sure that we do operation, real-time operation, safe and efficient motion planning and control. And of course, this box is a place like people like myself, trained in control, can do some interesting job. And that will result actually robot moving around, and motion robot will be interacting with human, and then make a feedback loop. Sensor again the measure what human is doing. So this is kind of human motion prediction, perception of prediction. And here what is shown is we are essentially making a history of the last end point, and based on that, predicting what kind of motion human will follow. Essentially, we made some neural network, and some part of the neural network, we introduced adaptive feature. So adaptive feature is for different human. We make training for one subject, one worker, but different worker may be coming. So in that case, some adjustment of the network output will be useful. So this is the task 1, environmental monitoring with human motion prediction. And then the control part, jumping to task 3, motion planning as an optimal control problem. We have robot dynamics, FR, human dynamics, FH, and essentially we would like to come up with control for the robot, GR. Okay. And in doing that, we would like to minimize certain performance index, robot cost function, and constraint is that we have robot dynamics, and constraint on control, you has to be confined in certain place, and also safety constraint on the system. We have to satisfy all kinds of constraint and optimize certain things. And among those constraints, most difficult one is safety constraint on the system, because human has got lots of uncertain aspects from robot point of view. So if we just look at this dotted line portion, exclude human, then the problem becomes a standard optimal control problem. So what we said was, okay, let's solve this part, red part, utilizing some standard programming approach. But just applying the standard method didn't quite work, because constraint include lots of non-convex optimization area, obstacle at many places. We still include some static object, and we would like to plan finding minimum X plan. And since area is not convex, so essentially this is what Chandu's work. She came up with feasible set, convex feasible set, series of convex feasible set. Do convex optimization in one region, and once you find one optimum point, then around there you look into another convex set. And you keep doing, and whether the minimum point has shifted enough. But this is the idea. And there is not a big change in the optimum from one convex set to another. We regard convergence has taken place. So in this way, we can have developed some nice plan for over the whole trajectory, okay, horizon, time horizon. So once we have this kind of feasible set algorithm figure out what is the optimal path, when robot is actually moving, robot has to make sure that safety is assured with dynamic object. So in this case, this figure explains human and robot. Human is a sort of the dynamic object, a dynamic obstacle, and we are doing robot control. And if, relatively speaking, human and robot stay in the blue area, we know that it's safe. Collision will not take place. So at some point, we are in the safe region, but we predict that the human will go out this region, go downward. Then we have to do something about robot. Robot has to move toward left, so that relatively speaking, relative position, robot and human will still be safe. And for doing this kind of check in real time, the essentially safety index was introduced. So phi is a function of relative distance and so forth. And as long as safety index is negative, we are safe. So from measurement, if we regard that safety index is positive, we would like to make sure that safety index will be in the direction we define u such that phi dot becomes negative. So it will push back to the safe region. So this was also called safe set. This was also invented, devised by Chan Liu, and it's safe set algorithms. So idea is that part, convex feasible set algorithm will figure out what will be the optimum u, best u. And then when safety is considered, we add safety controller. And the idea of safety controller is if we have safe control, if u is outside in the unsafe area, we try to pick up the safe control from the safe set, which is closest to the optimum UR. And in that way, we can achieve very safe maneuver. We demonstrated all the ideas by making some simple setup. So this was the last part of the project, NSF project. We had 2 workers and 2 robots, and station 1 essentially doing robot and worker is assembling something collaboratively, and robot 2 is essentially carrying one piece of object from one worker to another without collision. So this was a last part of the NSF project. Now, along this line, Chan Liu, after moving to CMU, she continues. So this is, again, conditional behavior prediction, what she is doing. And idea here is when the robot does things, he observes what human may be doing and decide motion. But the truth is, if robot does something, human will react. Okay, so take that kind of reaction into account. So account for influence on human and making that make sure that everything is safe. So she has a paper at ICRA this year. ICRA is, I think, almost next or in May in Yokohama. So she will be presenting this work. In terms of flexible automation, many kinds of small amount of product. Flexible automation was one reason for human-robot collaboration. But Min Hui, then, she also graduated my lab. She was doing PhD research on computer hard disk drive control. But after moving to Buffalo, she started looking into this human-robot collaboration. She said, okay, instead of assembly, disassembly should be more interesting because disassembly, there must be all kinds of hard disk drive coming in for disassembly. And each has got different firmware, size, and so forth. So I think that idea was received well by NSF. So she has got a series of NS funding, and she has got several interesting papers at IEEE transaction and also conferences. So this human-robot collaboration, one interesting application area is disassembly, which I didn't really pay attention. But there are lots of cases you can work on as a human-robot collaboration. Safe online gain optimization for Cartesian space variable impedance control. This is the group of students. Essentially, impedance control is a very popular topic, but interesting challenge is how do we set impedance for the best performance, and time-varying environment, how do we adjust impedance? So there are lots of interesting questions, and they brought in some kind of new method, the control methodology to answer these questions. Previously, adaptive control, reinforcement learning, optimization, all kinds of things has been tried. But in their work, they introduced the reinforcement learning type of thing. But on top of that, essentially, they formulated as a sort of optimization problem by introducing a kind of interesting dynamic equation to reflect the situation. And also they integrated the collision avoidance safety constraint inside impedance control by making impedance variable. So the problem they wanted to address is obtain optimal impedance gain in real time and establish safety constraint. And this is a kind of structure they came up. Low update rate, the optimization, and for safety, like every case, safety the consideration has to be accomplished at very high frequency because unsafe situation can come any time. So high update rate gain adaptation for safety. By the way, this type of consideration is also common in autonomous driving. We have some kind of layered approach. To deal with safety, we have the high frequency model predictive control, but for planning, we have low frequency predictive control and so forth. So the first step is to introduce mathematical model for optimization of the gain, starting with the standard impedance control equation. The equation was rewritten. E dot is still the state variable, but put G2XU, U is the impedance gain, and G2 is kind of all state. So instead of trying to keep the system linear, we put equation in this form. Then the good thing is U, which is impedance gain, appears as input vector, part of the input vector. So it becomes more possible to do real-time optimization. And doing real-time optimization, we needed some performance index. And there they find that the finite time integral of time-weighted absolute velocity error is a good one. So it's a velocity error instead of position error and time integral over finite time. And this is a baby example. And we keep doing optimization, say, every t second. So this is not a case that we solve the problem once and you just apply that strategy from the beginning to the end. We keep updating what would be the best and apply. And by doing that, when the mass is brought into the environment, which is stiff environment, if we don't change impedance at all, the transient is not good. With our introduced methodology, we can achieve blue line on the light. Blue line essentially nicely coming to the surface contact without much oscillation. Instead of velocity, if we try to minimize the integral of error, we have red, which is this type of error criteria tend to overreact at the beginning. So then it starts bouncing, so it's not good. So baby example said that this is a very good criteria. So we introduced this criteria. And to deal with constraint, we use so-called barrier function. Barrier function is a very popular approach in this type of problem. So if hx greater than 0, this first condition is satisfied, first line condition is satisfied, it's safe. But this hx greater than 0 does not involve any controlling signal, u. So we have to somehow introduce u. And there is some theorem to make hx greater than 0, the time derivative greater than 0, actually h dot x plus alpha h, that becomes 0. And if u shows up, you can make u to satisfy this nonlinear or this inequality constraint. If u still does not show up, go through the same process again, and it results in the strategy to select u. So we did this kind of thing, and the performance looks good. Constrained, constant gain baseline. Oops. Keep bouncing. Adaptive is good, but this method can make really nice and smooth transfer. I think I have to quickly move. And also collision avoidance, it was incorporated. With collision avoidance incorporated, without collision avoidance, robot can be easily pushed out of the boundary. But if we can go to the methods that we just developed, as we come close to the edge, impedance is increased, so robot resists to that motion, external force to go outside. So this was achieved. Efficient sim to real transfer was something. Robot need physically engage with environment. Robot manipulate object by applying suitable contact force. And traditional method is human expert, really program robot. So here we wanted to do learning-based approach. To make a little long story short, students succeeded to make a nice learning-based approach. It consists of offline learning phase. Here offline, they do training by simulation-based learning. Then in online, further tune that policy based on sensor information. And as a result, proposed method in the center, peg insertion. Of course, this does do a good job for the trained scenario, but it does do a good job for some different task. Yes. And it was even achieved something like screwdriving situation it could handle. Okay, I think I will skip this. The multi-agent interaction generation with imagined potential game. This is how we may solve conflict resolution when two agents are coming close to each other instead of bump. Someone has to yield. So that kind of collision will never take place. This is fairly new paper and it will be presented in June at SCC. If you are interested go to SCC proceedings and take a look. Now, on autonomous driving side, we have been doing model-based control and machine learning, their combination. So, for example, in this problem, something element involved is around the vehicle, we would like to do some sensing, estimation, and control. This is a type of problem when I was doing automated highway systems around 1990 probably. Around that time we are doing this kind of research. But modern autonomous driving comes with the perception, prediction, motion planning, and sensor is more generally detection problem, and tracking, localization, perception, map information. So it's a very, in our holistic problem with almost everything. Perception is that we have to recognize where we are, what kind of obstacle we might have. Then prediction is how the other car may be making motion. And according to the prediction, we have to make motion planning. And on the infrastructure side, we have to think about HD map, data pipeline, simulation test. So all kinds of elements in the autonomous driving research. So we have kind of test vehicle developed for the lab and simulation tool. And it's not really the most professional compared to some automotive companies. They have better simulation tool, hardware in the loop, experimental setup, but we have made our own version. And one aspect is that we really looked into integration of model-based control and machine learning. Model-based control still very traditional, so we know the robustness condition, stability condition. By having model, we have mathematical foundation. Machine learning, the idea is we just try to find the strategy based on the lots of simulation learning. And some people say model free, but it's not, that becomes a limitation also. And also long time to learn. And so taking advantage of combining good part of model-based control and machine learning, we should be able to do some nice things. So learn plans by machine learning and determine real-time control by model-based control. I think transfer learning may be possible by robust control theory and learn key parameters of planar controller. Little bit old paper, but this is zero-shot deep reinforcement learning driving policy transfer. Because the idea here is the reinforcement learning essentially learn action given state, so make this loop. And we learn in the test the learning environment. But when you actually do test, implement on real vehicle, real situation may not be exactly the same as the training situation. There may be disturbances, vehicle model is different, so the vehicle react little different to the input command, and also disturbance due to wind, some super elevation, that kind of thing affect the actual motion. So robustness guarantee is very important in real-time application. We do a good job as a human driver if we take a license driving using one car, and that skill can be utilized for almost any kind of vehicle. When we rent a car, we try to rent some new models that we never drove. That we do, but I think we can do a decent driving because we can easily know the good basic part and make adjustment to the difference. So we try to do this kind of thing by computer, automated systems. Zero-shot robustness interpretability can be all achieved by some robust control method. So block diagram sense, we explain that we have source domain where the learning is done, and we have target domain. Normally, in the test environment, target domain shows up. Now, if source domain learning was essentially from the observation road shape to the pedal steering angle, that kind of input. If we just learn that kind of thing, that's not a good thing for robust control because it's too much vehicle dependent. But if we learn what will be the given the road, what will be the good reference trajectory to follow, it's not necessarily just go center line. When we do change lane, what is the reference trajectory we should follow? If we learn reference trajectory, essentially robust control can come in to achieve following reference trajectory under the disturbances as well as the variation of the dynamics of the vehicle. So this is a kind of simulation, but the baseline is nice. Much of the training dynamics, test dynamics, it moves nice. But if the dynamics may be different, but if robust control is added, essentially the motion is remain almost the same. On the other hand, if we don't have robust controller and dynamics difference, vehicle might crash to the wall. Okay, so we devised this kind of approach, and here plotted as an effect of the parameter variation, side force due to wind and so forth. As disturbance increases, parameter variation increases. If we do not do robust controller addition, performance keep going down. That's blue. On the other hand, if we add some robust control methodology, we can attain fairly flat same performance. We did some experiment in this case in the near UC Berkeley campus. There is a test field that we can do this kind of experiment. And this is related, closely related to some human-robot collaboration. What is planning, learn planning, what to follow in action? And essentially we came up with the structure in the right-hand side, integrated planning and control module. Policy layer set the basic policy, what kind of trajectory path we should follow. And we used the neural network to develop policy layer kind of answer to us. And once neural network is learned, neural network is itself is very fast to implement. So because it's just a nonlinear mapping. So nonlinear mapping gives some reference trajectory, but if some obstacle shows up, if the vehicle has to make some fine adjustment, execution layer has short-term optimization, short-term model predictive control, for example, and do a good decision-making. This is the neural network part. We did some imitation learning, idea of imitation learning, some key variables, how they should be combined and give a best output waypoint, then execution. Okay, so let me just finish. Okay, this is for the courtesy, like this is something we are doing. The AI race pushing the limit. It's kind of interesting. It's a game environment, but there are lots of interesting research challenge. Okay, so we have lots of projects, and funding come from government, NSF, or state agency, PASS, or even external foreign government. We interact with Hong Kong Center of Logistics Research and private companies. So this research was really done by my bright student, and I have graduated quite a few of those students. I think by now, probably 139 should be revised to 145 or something. Thank you very much.
All right, thank you for Professor Tomizuka for the talk. I think given the time, maybe let's just take 2 questions from the audience.
One question?
Yes.
So that paper that you showed, so the imitation learning with unit trajectories for cars. So you use neural networks to imitate the expert behavior. But then, what if the input, what if the feature input was out of distribution?
Input was something like the vehicle position, where is the wall, where is the next lane, and etc. I think I have a series of items listed here. These are the features. Yeah, input. Yeah.
Then what if for a certain input, you get a really bad trajectory from the neural network because these statistic inputs were never trained?
Yeah. Yeah, given, so actually once it's trained, they become the input to the network, and it will generate, follow this trajectory.
Hey, be quiet
Okay.
in the back of the room as you leave, please.
Okay, cool.
Okay.
Nice.
I think we published paper, so if you are interested in, nice if you can take a look of the paper. Okay.
Cool.
Okay. Yes. Yes, sir. Okay.
So follow up on his thing. I think maybe what he's getting at, I'm not certain, is if the inputs are sufficiently, if the inputs somehow lead to a bad output, what role does this MPC play in sort of ensuring that at the very least, if there's bad waypoints output, that you can still achieve some form of safety?
Actually, if the reference waypoint does not exist, if we jump into the model predictive control itself, if you try to implement its non-linearity, etc., it's very computer intensive. So you can only go for short time horizon. Then that's not good. If short time horizon, it may even crash immediately. But having this kind of reference trajectory, it's more, does not do some crazy plan. I still have to follow this. So try to minimize deviation from natural trajectories that I can follow. But here is obstacle, so I should really bypass. And the simulation part I didn't show, but it clearly shows the advantage. Model predictive control ensures that I can safely maneuver